Laura. Thanks for the introduction, and welcome everybody to this presentation today, which is going to be, as Laura noted, the application of spectral accuracy to mass spectrometry for enhanced formula ID and mixture analysis. This is just a little presentation outline to know what we're going to be covering today. And the first thing we're going to talk about is we're going to talk about the importance of mass spec line shape calibration and the concept of spectral accuracy. The next we're going to talk about an example of using formula identification and the application of spectral accuracy to compound determination on a unit mass resolution GCMS system. From there, we're going to move to some application examples on single quad unit resolution LCMS instruments. And then we're going to move on to look at applications of spectral accuracy to high resolution MS. And then next, we're going to look at some actually very new approaches that have been developed recently for performing unknown formula ID on ultra-high resolution mass spectrometers. And then finally, we're going to look at some an example application of quantitative mixture analysis, which actually can be performed on both high resolution and low resolution mass spectrometry. And then we'll do a wrap up. Okay, let's get started. We'll talk a little bit about the fundamentals of and concept of spectral accuracy here. And the first thing to recognize is that the raw signal that we see from most spectrometers is typically reduced to centroided data before it is presented to the user for analysis. And we can see a typical centroid plot for some data from a quadrupole instrument at resolution of about 800. But it's very important to understand that the actual data that is collected from any mass spec instrument is actually a continuum. It's a continuum scan, which is typically processed and eventually presented to the user as centroided data. And this is commonly known, it goes under a number of different names depending on the vendor and who you're talking to, but it's typically known as profile or raw scan data. And if we look at the centroided data, and at first look, it does look like pretty much a theoretically calculated mass spectrum with intensities at the given mass locations. However, if we look a little bit more carefully, especially, for example, we look at the A+1 cluster, we actually see that it consists of a number of multiple isobars, indicating the presence, in this case, of carbon-13, nitrogen-15, S33, deuterium, and oxygen-17. And after we centroid the data, of course, these smaller peaks, which are key to the elemental composition information, are lost once we centroid it. And also, if we look under A+2, it's even richer in the information it provides. Again, the point is that after we centroided the data, we've virtually thrown away that valuable information. And it turns out that information can be very useful even in unit resolution mass spectrometers such as single quad GCMS and LCMS systems. And in fact, if we look at a variety of different compounds with different elemental composition, all at approximately the same mass value, clearly there's a different isotope pattern that can be used to distinguish between these formulas. And this starts to lead us into this concept of spectral accuracy, which reflects our ability to accurately model that isotope profiled information. And of course, as you can see, that the various isotope distributions are what gives each particular formula its unique signature. let's take a look at conventional mass spec calibration and how it operates. This is a unit resolution typical quadrupole scan, and what's done in most mass spectrometers is that we know what the theoretical mass spectrum should look like, and this is just a theoretical mass spectrum that's involved with a mathematical function like a Gaussian to make it look approximately like that of the measured spectrum. And in a conventional mass spec calibration, what's happened is we calibrate simply the mass position. But if we compare these two isotope profiles, since the instrument itself, the mass spectrometer, uses electromagnetic fields effectively as a lens, it's not a perfect lens by any stretch of the imagination. And so the actual line shape that's imposed upon the mass spec measurement is really undefined. It's not known. It's not a defined mathematical function. And so if we try to compare this isotope profile with theoretically generated isotope profiles, they tend to look similar, but they don't match up very well. Okay, and this ability to match the measured and theoretical isotope patterns is what we term as spectral accuracy. So let's look at a very different kind of calibration. And in this particular calibration, we'll see how it works, because we're going to correct the spectrum for both mass accuracy as well as what we call spectral accuracy, or the actual profile itself. So the first thing that we do for this calibration is we have to measure a known ion standard. It can be anything. It just has to be relatively close in mass to the ion that we're going to be ultimately analyzing. And the first thing we do is we estimate the approximate resolution of the data. That's pretty easily done. You look at the monoisotopic peak. And from there, what we do is we choose a mathematically defined line shape. It's a perfect line shape. It could be, for example, a Gaussian. That's very common. It doesn't have to be, but we can choose a Gaussian, which has approximately the same line width as our measured line width from our mass spectrometer. The difference is, of course, now it's an analytically defined function, unlike the measurement in our mass spectrometer, which is an undefined function. We don't know what that line shape function is. The next step is since we know what the standard is, we can calculate a theoretical mass spec, which has infinite resolution, and you can see all the isotope peaks and all the isobars. And the beauty of mass spectrometry, unlike almost any other analytical technique, we can very accurately calculate the spectrum because we know the masses of all the elements, and we also know the isotope distribution for the most part in nature. So this makes mass spectrometry very unique. We can actually calculate any mass spectrum. The next thing we do is we convolve that line shape that we chose, that pure Gaussian line shape. We convolve it with our infinite resolution theoretical spectrum. And now we've come up with a calculated true spectrum, okay, which resembles that resembles the resolution of our measured data, but it has a known line shape. And many of you have seen spectrum calculators built into the vendor software, or even online calculators that let you accomplish this. So now what we do is we compare our measured standard from the mass spectrometer with its undefined line shape to that of the ideal or the true calculated spectrum. And from the comparison of these two, using the magic of a little bit of linear algebra, we can actually calculate a function which explains the difference, and that's that green squiggle that I just drew up there. That function explains the difference between those two curves, the perfect true mass spectrum and the uncalibrated raw mass spectrum. And the function explains not only the difference in the line shape, but also the mass position. So it actually will correct for both the mass position and the instrument line shape. So the next thing to do is once we've had this calibration function, so we've run a standard on our mass spectrometer, and we've saved this function away, and when we go to measure our unknown, we simply apply this calibration function to the ion of interest. And here, just a graphical representation showing how this function is applied to the measured mass spectrum to give us a calibrated mass spectrum that is calibrated not only in mass position, okay, but also in its line shape. So it looks very much like that calculated spectrum using a pure mathematical line shape, because that's what this calibration function accomplishes. And we can compare that to the raw measured mass spectrum from the instrument. And again, you can see that we're correcting for both the mass position and the actual line shape as well. So what does that give us? It actually gives us a number of interesting opportunities to take advantage of the calibrated data now. Probably the most interesting aspect of it is it allows us to obtain very high mass accuracy, even on relatively low or unit resolution mass spectrometers such as single quad, GC, and LC-MS systems. The typical specification for mass accuracy from the vendor for the instruments, for these types of instruments, is typically on the order of about plus or minus 0.2 to about 0.5 Daltons. Once we've calibrated the mass spectrum, even on unit resolution, we can attain very good mass accuracy. The reason is because normally when the vendor software centroids the data, it only uses the information over the peak. Since we now know what the instrument line shape is, we can actually fit a curve over many points. And these instruments, even at unit resolution, have very good precision. Okay. The problem is that our ability to accurately locate the center isn't possible. But by calibrating to this known line shape, we can actually fit that line shape to the unknown spectrum and get very good mass accuracy even on lower resolution instruments. And in fact, it's been shown that we get about 100 times better mass accuracy using this approach. So that opens up some interesting doors for low resolution instruments to enable them to actually to perform feats that they really weren't capable of performing before. And we'll look at some of those examples. But the next thing I want to talk about is this concept of spectral accuracy. Since if you look at the red trace, it's a little hard to see because it actually the theoretical or true mass spectrum is overlaid right on top of it. But because we've calibrated to this known line shape, and we've also have accurate mass in even in our unit resolution instrument, we can now actually compare the full isotope pattern. That gives us a whole nother dimension to work with. So we can not only identify an unknown ion based solely on its accurate mass, but also on what we call the spectral accuracy. So we've calibrated the instrument now for both mass and spectral accuracy. If you're interested in the details of the mathematics here, it's actually quite simple. This is covered in a feature article published in Analytical Chemistry. It's available on our website, which is dated back to 2010. So it's by no means a new concept and has been well established in industry. Okay, let's move on. We're going to look at some applications of this technology, this calibration technology, for a variety of different types of instrumentation from, as I said, from low resolution all the way up to very high resolution instruments, and then moving on into mixture analysis. The first example we're going to look at is the formula ID and accurate mass compound determination with unit resolution GCMS. the thing that's sometimes the most difficult is we need to provide a calibration standard. One of the beauties of GCMS is a lot of the instruments have a built-in calibration gas, which is PFTBA, and that's used for the instrument tune. And the instrument tune itself is actually a step that you do on your instrument. It's independent of what we do. We do it on the data after the tune. Okay, so our calibration is quite different from a tune. But the important thing is the availability of that calibration gas makes it very easy to perform a comprehensive calibration on a GCMS system. And in fact, some of the commercial GCMS systems allow you to set up in the method a point in time where you can control the injection of the calibration gas. And for example, this is an example that shows the run. At the end of the run, the oven cools down, and part of the method is it will actually inject a little bit of the calibration gas. We perform our calibration, build our calibration equations across the whole mass spectrum, and we apply that to the run. We have a fully calibrated run. You don't have to do the calibration within the same run. That's one way to do it. You could also, the instruments are quite stable over a period of a few days, so you can typically run a calibration in the morning and then perform your runs throughout the day, and the calibration holds fine. This is a very simple example. This was actually a blind test from a forensic laboratory, which was really interested in testing the ability to do formula ID on a GCMS. And it's a white crystalline powder that we were given. We actually don't have any instruments here, so all these data were measured by the customers on their instruments. And this particular sample was provided by a large forensic laboratory. And the peak in particular that they were interested in, one of them, was a peak that elutes at 8.7 minutes. So what we do in the software is we simply average across that peak, and that produces, and we apply our calibration to that mass spectrum, and we now have a fully calibrated mass spectrum that's calibrated in both accurate mass as well as spectral accuracy. So one of the things we can do is formula ID of the molecular ion to recover the formula. And so we look at the peak at 240, which happens to be the molecular ion peak. And what we do is we simply click on it, and if those of you familiar with accurate mass instruments, what we'll do is we'll do a formula search, okay? So you know some chemistry, you have some pretty good idea of what the elemental composition is. You can, of course, expand this if you're less certain about the elemental composition of your sample. All this does, it makes the formula list get longer and longer. And since we've calibrated an accurate mass, we tell the software to go off and find all formulas that are within a mass tolerance window. In this case, we used a fairly wide window of about 20 millidalton, and we produced a list of formulas. And in fact, you're always going to get a list of formulas, almost always. Even if you're using high-resolution instruments, especially at a higher molecular weight and more complex elemental makeup, you're going to get a long list of formulas. So the question is, what formula is the correct formula? And this is where there's usually a long process of trying to understand and looking at orthogonal techniques to help us evaluate it. Well, one of the orthogonal techniques that we can use is, as we've mentioned, is the spectral accuracy. So if you see the column on the list there on the right, it says spectral accuracy. And I should mention that it's a relative measure of the goodness of the fit of the true or the calculated mass spectrum to the calibrated mass spectrum, where 100 is a perfect match. Of course, we always have noise, and usually there's some level of background interference. So it's never a perfect 100. But when you get up to around 99%, that's a very good indicator of an excellent match. And we'll look at some visuals of this. So what we can do is we can actually sort the list of formula found in that mass window by spectral accuracy. So the ones that percolate to the top are the most likely candidates based upon their spectral accuracy. So what we're doing here is we're using both mass accuracy and spectral accuracy to whittle down our unknown formula ID choices. Just to give you an idea visually, this actually compound was correctly identified. The formula was Tetramine, which is a potent poison, rat poison. And there was 107 formulas that came out of that 20 milldalton Windows accurate mass search. So if we look at the top left there, what we have is the overlay of the red, which is the calibrated mass spectrum, and the true mass spectrum, in other words, the calculated mass spectrum of that formula. And you can see it's in black, and you can see that it overlays very, very precisely over that unknown. So if we look at the second best match, which is the lower left, which says second best match, the spectral accuracy is close, but it's not quite the same. It's a little difficult to see, but you start to see at A+1 and A+2 slight deviations. And then as we drop down to the 10th best match, you can see clearly at A+1 plus A+2 significant deviations in the isotope profile. So this is a very sensitive tool to assist us in gaining greater confidence in our formula ID for low-resolution instruments. So just a little bit about sum up on the GCMS Lineshape calibration. It will enable these types of instruments to produce accurate mass formula ID with very high spectral accuracy so that we can do elemental composition determination. It's very easy, or we can even automate the calibration process. So from the user perspective, it's a very easy experiment to perform. Of course, we have in GCMS, we have GCMS libraries, which are routinely used for identification of unknowns. And this approach doesn't replace it, certainly, because in the GCMS library search, you look at the fragments, and so you can actually get exact structure information. But it's a piece of complementary information that can be used in the GCMS search. You can even use it as a filter by using the accurate mass capabilities to eliminate a long list of library search hits. So it can also provide unknown ID and structural clues because the fragments are calibrated as well. So if it's truly an unknown and if it's not in the library, we can utilize this information to help work us back to what the actual structure might be. Okay, let's move on to LCMS, and this is perhaps maybe even more interesting because since LCMS we're using soft ionization techniques, we typically don't get the fragment patterns that we do in GCMS, which can be used for searching in combat formula or structural ID. We typically only get the molecular ion. So here it can be really a strong tool to help us do formula ID on these routine instruments. This is an example that from a pharmaceutical lab. This is looking at a common thing to be done here is looking at impurities in a drug, and so you can see the parent drug, which is a statin. They're at retention time about 4.4 minutes, and all those other peaks that show up in the chromatogram are some types of impurities. So the idea is we would like to be able to identify these on a unit resolution instrument without having to resort to a high resolution instrument for routine applications. Well, first of all, how do we develop a calibration for LCMS? And GCMS, as we noted, it's very convenient. We have a built-in calibration. Some of the LCMS instruments also use standard tune solutions, which we can take advantage of to build a calibration. The other approach is we just can use, since we know what the parent drug is, and it's producing a series of ions and adducts over a significant mass range, we can actually use these ions, since we know them, as an internal calibration set. And that's exactly what we're doing in this case. Once we've applied that calibration and we analyze the other unknown GCMS peaks, what we've done here is we've just created a table which shows the identified formula of the formula for the unknown, and we've also given the mass error in both milli-Daltons and ppm, the spectral accuracy measurement, and the formula rank. In other words, after we apply both our mass calibration and our spectral accuracy calibration, what's the rank? Where does it go? Where does it go on the list? And then the last column there just shows the number of total formula that were searched within that mass window. And as you go down, you'll see that typically the compounds that came out on the top as the top hit typically have good spectral accuracy, close to about 99%. If we go to the fourth one there, the fourth column there, we see a significant drop-off in our spectral accuracy. And notice that the rank is also, we didn't get the top hit, we got it at the fourth hit. Not bad, okay? But that 94.5 value is another indicator that potentially something else is going wrong. And that something else is usually a background or an interference. And of course, there's no substitution for high resolution. We're trying to utilize these lower resolution instruments, but they don't have that resolving power to reject the interferences. But still, the spectral accuracy value actually gives you an indication of the confidence of the match itself. This is just a list from one of the impurity peaks at 3.3 minutes. This shows the output of the search results of the formula ID results, and with the top hit here being 99.4% spectral accuracy, with about 2 milli-Dalton mass error, and the next best hit drops down fairly significantly down to about 98.8. So that gives us a fairly good confidence on that we have the right formula there. And just a visual here, this basically shows the uncalibrated data from this particular LCMS system to the calibrated data. So again, it's very apparent that what we've done here is we've not only calculated to accurate mass, but perhaps more importantly, we've also calibrated to a proper line shape. Okay, good, move on. And what I'm showing here is an overlay of the calibrated, which is the red, to the calculated or true mass spectrum. And they're overlaid, they lay pretty much exactly right on top of one another. So again, this is the power of using spectral accuracy for unknown formula ID. If we go down to match number 3, you can start to see some variations in the overlay of the calibrated and the calculated mass spec. Again, this just validates visually the confidence that we have in the actual results. So in summary, in terms of unit resolution LCMS, it enables accurate formula ID utilizing both accurate mass and high spectral accuracy. It's a very good tool for routine work, for well-separated samples. If you have more complex samples, because you have a lower resolution instrument, it's not necessarily going to get the job done. You're always going to do better with a high resolution instrument. But for day-to-day applications, for example, in organic synthesis ID, pharmaceuticals and impurities, the example we just looked at, consumer products, food safety, this can really turn a workhorse LCMS system into a significantly more powerful tool. Okay, let's move on to high resolution mass spec and see how we can apply spectral accuracy to help us out there. And in high resolution mass spec, the interesting thing here is we can actually perform our calibration without measuring an external calibration standard. The reason for this is that in high resolution MS, we have a well-resolved monoisotopic peak. And of course, by definition, that peak is isotopically pure. It's a single line. There's no isobars in there. So we can actually use the monoisotopic peak as the calibration standard for the entire ion profile. Okay? Very simple concept. And it works very much like what we did by measuring an additional standard. What we do is we look at the isotopically pure peak. Again, we choose our line shape function, and then we go and calculate our correction function, and then we apply it to the high resolution data. So in a high resolution measurement, we've already got high mass accuracy. What we do here is we only calibrate it to high spectral accuracy. So the blue line there shows the calibrated data, and the black line there shows the raw or uncalibrated data. And if we compare that to the true or theoretically generated spectrum, you can see the match is very, very good. So now we can take advantage of spectral accuracy in a high resolution instrumentation. And this is just a very simple experiment. This was actually given to us by a vendor who was evaluating this some years ago. And it was a simple LC-TOF infusion of a mixture of compounds. And from that, we choose an ion. This is actually a fairly high mass, and as everybody knows, as you go to higher mass, you're going to get more. You're going to get a longer and longer list of formula candidates. So we're going to perform what we call our S-clips, which is our self-calibration routine on this particular data. And this is just a screenshot. What you do is you simply click on the monoisotopic peak, you tell it to search, it pops up that dialog, you do the search, and you obtain the results. Very simple. And this is a typical list of results. Again, we're sorting the list of formulas. And in this case, we had a 4 ppm window, and we had 75 formula candidates. And the top of the list has very good spectral accuracy. Yes, it turns out to be the right formula. That's not always the case, but it's pretty much guaranteed to be up at the top of the list. And of course, if we have problems, we'll see in some future slides why spectral accuracy can be a very good diagnostic to warn you that either the instrument's not behaving properly or that maybe we're looking at a mixture. And that's something that's always a challenge. So if you look at the top hit, we are overlaying again in green the calculated, and black is the calibrated. You can see the top hit has very good match, overlays almost exactly on top of it. And again, if we look at the second hit, you can see a A+2. There is some significant deviation in the pattern. So we're really using this isotope pattern calibration, spectral accuracy, as a fingerprint, because each formula is going to have not only a unique mass position, but it's going to have a unique isotope fingerprint. And we can use that information now very accurately. Okay, let's move on and let's talk about very high resolution. I'm talking about on the order of the data that we're going to look at is about 240,000 in terms of resolution. And even in the highest resolution instrument, we still, with very high mass accuracy, we're still going to get a list of formula candidates. So it's not uncommon for people to look at the isotope patterns visually, but by calibrating them, we can do a much better job. And in fact, as it turns out, we can take advantage of mass spectrometry at high resolution to really get very definitive fingerprints. And it's interesting if you look at M+2 here. Okay, this is actually calculated from vendor software at a resolution of 500,000. You can see at M+2, and again, note that the scale here is at the top there. That arrow designates 5 milladalton. Okay, in terms of the scale. So this is very blown up around M+2, but we see beautiful we can see some beautiful and very distinct isotope patterns in this area, and it's a very unique fingerprint just by looking at high resolution at this particular M+2. And why don't we just take advantage of these fingerprints? Well, we can do that. We can calibrate the spectrum using our monoisotopic peak. But when we do our spectral accuracy match, we can just look at this one location. We can ignore actually M+0, M+1, and in fact, it's good to do that because it actually skews the results. And by just looking at this distinct pattern at M+2, it's an incredibly powerful indicator for the correct formula, and we'll see that in the next slide. So what we've done here is at high resolution, we've made our formula measurement, and we look at our spectral accuracy. It's not probably as high as you've seen some of the other examples, and I'll get to that in a second. But the important thing to note is that if you look at the results for the first formula candidate and the second formula candidate, there is a huge jump in the spectral accuracy. Okay, from about 95 down to about 75. It's a huge distinction, and the reason is if you look at the graph on the right for the number one match, you can see a pretty good match. Okay, it overlays very nicely, but as soon as you go down to the second match, these isotope profiles at high resolution at M+2 are so distinctive. It makes it very easy to confidently do a unique formula ID. This is a very powerful tool. Actually, this is some work that was done by one of our customers, and that's going to be soon to be published over the next few months. Very powerful approach to unknown formula ID, and he's done this on a whole variety of compounds they test internally, and it routinely will uniquely identify unambiguously the top formula candidate and the correct formula candidate. So just a little wrap up on the high resolution Lineshape self-calibration. The neat thing is no calibration standard is needed. We have an internal calibration standard, which is the monoisotopic peak. It can provide a pretty significant improvement in the correct formula ID, even at high resolution. And at high resolution, our ability to just use the M+2 peak alone can provide really distinct, unambiguous breakout formula ID. However, you do have to be careful about instrumental artifacts. They have to be carefully controlled. For example, in certain trap type instruments, there are space charge effects, and when you have ions that are close to each other in that racetrack, they will significantly distort the spectra, and you'll lose the ability to get good spectral accuracy matches. And that's actually something that we'll be publishing in the near future about how to optimize that. Okay, let's move on to our final topic here, which is quantitative mixture analysis. And this can be applied to both high and low resolution instruments. And if you look around at other types of spectroscopic techniques, in particular near-infrared spectroscopy, UV vis, even mid-infrared spectroscopy, it's being used today as a very powerful tool for the quantitation of unresolved mixtures in spectroscopy. And typical applications you'll see is agriculture. If you buy bread, when the farmer sells his wheat, he measures the moisture, he measures the protein, and he measures the fat, and that determines the price of the product. So it's important to quantitate those things so he gets his money. And near-infrared is used typically to do that. The process control in small molecule pharmaceuticals is a very popular application for Raman, near-infrared instruments, for food, for measuring, for example, fat and moisture in cheese and meat, and also applications in pharmaceutical and chemical. So it's a very powerful spectroscopic tool. Unfortunately, when we move to mass spec, there's a problem, okay? The problem is that the line shapes, as we discussed, are literally a moving target. We can't, if the peak shape shifts, any calibrations that are built for doing this mixture analysis change, and we have to redo the whole calibration all over again. But in our calibration approach, we've calibrated the line shape, and that will enable us to do complex mixture analysis. And the interesting thing is that the accurate since we can calculate now a mass spec based upon using that same line shape, there's actually no need to go off and do a physical measurement of the mixtures, which is typically what one has to do in the near-infrared and the Raman and the mid-infrared. We don't need to do that because we actually can calculate the spectra. Again, one of the beauties of mass spectrometry. So this allows us to build a calibration model which is where we don't have to use a training set, okay? And for example, it's typical in those areas of spectroscopy that we use techniques such as PLS or ANN or MLR or CLS, all mathematical algebraic approaches to building calibration models. We don't need to do that because we know what the spectra are going to look like because we've calibrated the line shape now, and we can calculate all the spectra. Again, beauty of mass spec. So let's look at an application. This is an application of peptide deamidation. Obviously, it's a very big concern in the development of biologics. We need to be able to quantify the degradation impurities and characterize them for both development work and also in the formulation of the biologics. And one of the very common degradation pathways that we're going to look at is deamidation. And you actually can get two deamidation products from asparagine, which is aspartic acid, and isoaspartic acid. And so keep that in the back of your mind. And the typical approach that's used, this is the current kind of gold standard, is we do a tryptic digest of the protein, and we use LCMS to do the separation and the mapping. And this is really the gold standard. So we digest the protein, the smaller peptides. We develop a robust method to achieve chromatographic separation between the native and the modified forms of the peptides. And then we perform relative quantitation by LCMS peak area integration, usually based upon accurate mass extracted ion chromatogram. So this was a customer sample. He developed his method. It's a rather lengthy and tedious, and these separation methods can be quite long. Can go almost 2 hours long. This one went about 70 minutes. You can see at the top there, that's the total ion chromatogram of the entire run. And then what we do is we use an extracted ion chromatogram, accurate mass extracted ion chromatogram, to try to locate the native and the deaminated species. And of course, they're separated by they're fairly close together in mass, so that's why we require an accurate mass instrument. And when we run it, sure enough, we see two peaks here in the middle. That's been identified as the native form, which elutes at about 63 minutes. And also the deaminated form, which elutes slightly after that. So it looks like we have a nice separation, and we can do relative quantification of the native and the deaminated forms. However, we can do a kind of a check on that. And what we've done here is we looked at the pure peptide, okay, not deaminated, and we look at that peak, and we actually run our match here, and we're actually not, we know what it is, so we don't have to search on on a range of formulas. We can simply search on the formula that we're interested in. What we're really interested in getting at is the spectral accuracy. Because if you think about it, if the spectral accuracy doesn't match, that potentially means that we don't have a pure compound. So it's a really good diagnostic tool to understand whether we're actually looking at a pure component or a mixture, or we're looking at non-linearity in the actual instrument measurement. In any case, it can be used as a real good indicator. And if we look at the spectral accuracy here, and you can see the overlay of the calibrated and the true, it does not match very well. The spectral accuracy here is about 91.8. That's a flag. Okay, that's telling us that there's something wrong here. And again, the spargenine, produces two isomeric forms, and there's a possibility that they can elute at different positions. And indeed, what we can tell the software, if we suspect that we have an interference, we can simply perform our formula search on that on the peptide, and we can tell the software to look for not only the pure component, but the deaminated species. And when we do that, and we then perform the spectral accuracy match, so what we have is we have a dramatic improvement in the spectral accuracy and a pretty good match. So what this is indicating and what the software is telling us here, if you look at the little table here of the concentration in the formula, the software can basically looks for the native undeaminated peptide, and it also takes into account the deaminated species, and it uses that spectral profile matching using theoretically generated spectra to match. And it can do that because we can calculate both. We just have to propose the mixture to it. And what it found is that it's actually only about 89% pure, and that indeed it contains about 11% of the deaminated species, probably the other isomer here. So we thought we had a method. We thought we had a method working. Turns out that we don't. And this is a really good check to see to validate your results in this type of experiment. But interestingly enough, you'll see here at let's see, at A+4 and A+5, it doesn't quite match. There's some error there. And what's the other potential degradation pathway? The other potential degradation pathway is oxidation. So again, what we can do here is we can propose to the software to look for, in addition to the deaminated species, also the oxidized species. And now you have a near perfect fit. That gives you a really high degree of confidence that again, this is not a pure component. This is actually a mixture of native, deaminated, and a small amount down on the few percent level of the oxidized species. Okay. So that just shows you the power of spectral accuracy for really validating results that would otherwise go unnoticed. And I think the takeaway here is that mass accuracy is very important, obviously, in mass spectrometry. But spectral accuracy, it can be even more important for a lot of this work. It's a very powerful tool that we can add to our toolbox now. And the key is the Lineshape calibration enables us to help differentiate our formula candidates when we do accurate mass searches. And the elemental composition determination now is also, with this approach, it's both feasible and practical for routine use on a single quad. Again, emphasize, does not replace a high-resolution instrument, but it adds significant value to routine work on a low-resolution instrument, which could not otherwise be done. At high-resolution mass spec, we can use our spectral accuracy to eliminate up to 99% of our incorrect formulas. And finally, we can also use the spectral accuracy metric to not only indicate that there's a mixture, but also to potentially analyze the mixtures if we have an idea of what the other components are in that mixture. Okay, and with that, I'm going to pass it back to Laura, and she's going to read out some questions, and I'm going to try to answer them. Thanks again.
Fantastic. Thank you, Dr. Keel, for that informative presentation. It is now time for questions from the audience. As a quick reminder, if you want to submit a question, you can do that by typing it in the Q&A box, and you can find that on the right-hand side of your screen. Okay, so here's the first question. Does your approach offer any advantages in looking at larger multiply charged molecules where the monoisotopic peak is no longer the most intense?
This is an area that's very interesting to us. Actually, we believe it does. We haven't really done a lot of work in that area, but actually just having come back from ASMS and seeing all the interesting papers on large molecules, I think there's a lot of potential that we can bring. I think the current approach of what they call deconvoluting multiple ion species is flawed, and we believe that we could do a much better job of that. So the answer is we believe so. We are just starting to explore that area.
Can a TOF accurate mass spec be used for quantitative analysis? I don't know if that means using your software as well.
I think they're talking about quantitative analysis. This is something we don't do. We can do relative quantitation, as you saw in our example of our digested proteins. We've done this work also with, for example, labeled isotope work. We've also done it with other applications where we have mixtures. But in the sense of quantitation, as it's defined in conventional mass spec, there's not really much value that I think we can add there today.
How stable is the calibration for a quadrupole MS mass spectrometer, and how often do I need to recalibrate?
Great question. There's actually there was an interesting paper. It's actually available on our website that was published by, I believe it was Behringer Ingelheim, which looked at this problem specifically, and they did a very thorough evaluation on a single quad. I believe it was a GC instrument, and they found that the calibration would hold for a couple of days, certainly over a 24-hour period, no problem at all. So the calibration, I wouldn't do it that way. I'm just a little bit anal, so I would tend to do it more frequently than that. But modern instruments are very good, very, very precise, and very stable. So the answer is at least 24 hours, and in some cases a couple of days, although if I were to do that, I would want to quantify that on that particular instrument. They do vary.
This person asks, how can we attain spectral accuracy on a single quad, and what will be the limit as compared to using high-resolution mass spectrometry?
You're always going to do better with high resolution. There are some advantages to a quadrupole instrument, and there's also some disadvantages. One of the advantages is it has a very large dynamic range, very linear. That means we can apply this technique over a very large range of concentrations. Of course, they're not as sensitive as some of the multiplex instrumentation at high resolution, like TOF and Orbitrap. And of course, there's always the issue of mixtures, okay, or background. You're always going to do better with high res if you have complex samples. In a low resolution instrument, you're not going to be able to separate spectroscopically those interference techniques like you can in a high resolution instrument. The good news is that we can use spectral accuracy as an indicator of the occurrence of interferences or of unresolved peaks, but it doesn't solve the end problem for us.
Do we have to use the same class of compounds containing similar elements for calibration?
No, the calibration compounds do not need to be related at all chemically. The only requirement is that you want the calibration ion to be within a mass window of about plus or minus 50 Daltons from the unknown ion to be analyzed. So no, the chemistry it's independent of the chemistry.
What happens if the sample is complex with interfering ions overlapping the analyte ion in both retention time and M/Z?
Okay. Well, it's pretty much back to the question 2 questions ago. If you have an idea of what the contamination is or what the mixture is, you can propose to that, and we'll do a mixture analysis for you. But again, the spectral accuracy is an indicator of the purity of the system, so it won't necessarily give you the end right answer, but it'll let you know that beware. So it's a good diagnostic tool.
Great. Let's maybe do 1 or 2 more. How do I acquire data on an Orbitrap to ensure the best spectral accuracy?
Okay, Orbitraps, they are trap instruments. You do have to be careful about space charge effects. We looked at that M+2 peak there. If the ion concentration in the trap gets too high, you'll actually see the relative intensities of those peaks significantly change, and even the position of those peaks change. The key is to control the ion population. Automatic gain control in the instruments helps you, but actually we found that a lot of times you want to go even lower than the vendor recommended ion concentration. And actually this is some work that we're going to be publishing on how to optimize these types of instruments to get really, I think, some pretty exciting results in terms of unambiguous formula ID.
Fantastic. Well, we're just about at the top of the hour, so I think we should wrap up. Thank you so much, Dr. Keel, for that excellent presentation and for answering all those questions.
Thank you. Thank everybody else.
I also want to thank all of you in the audience for attending and participating in today's event. And I'd like to thank our sponsor, Cerno Bioscience, for making today's webcast possible. Today's webcast will be available for on-demand viewing through June of next year. You'll receive an email from LCDC alerting you when this webcast is available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. We hope to see you all next time. Goodbye.